Good morning. Okay, so I put there up on the board the very same thing that I had yesterday, which is essentially going over the very same material that we have in this handout. I used this abbreviated notation for the central extension of the symmetry of annuli, but it's the same central extension with C cross times Z, which I had before. And now I want to tell you a little bit about some of the structure that you get, that you have in any Carroll conformal field theory, and how you get it specifically from this setup. And the first thing that I want to tell you about is the so-called vacuum sector of the Carroll CFT. So we start from the simplest possible cobordism that you can imagine, which is the disk. The disk is a cobordism from the empty one manifold 2S1, and it's just what you think it is, just like the standard unit disk with boundary S1. The boundary of the unit disk is what I call S1. That's purely outgoing. And associated to that, well, this is a cobordism. So you look at there's a functor from the category associated to the empty set. Okay, what is the category associated to the empty set? That is the category of vector spaces, dimensional vector spaces. And in there is a specific distinguished object, which is the complex numbers, the unit of this category. And therefore, it makes sense to take the image of that object under this functor, and I will get a distinguished object in here. So we get vec, which is the same thing as C of the empty set, mapping to C of S1. And if I take this object there, this is in some sense the unit of that category, so it makes sense to call it 1. But there's going to be many things that are called 1. When I talk about it, I will call it 1 sub empty. 1 sub empty is going to be by definition the same thing as just this particular object. I can take one sub empty, which is an object in here, and I can map it in here, and I get an object that I'm going to call. So this category ends up at the very end of the day being equipped to the structure of a modular tensor category. In particular, it's a tensor category. It has a unit object. That unit object deserves to be called 1. And I'm going to call it a different font of 1. That's by definition, 1 in here is the image of 1 in here under this functor. Really, what I care about is the image of this boldface 1 under this forgetful functor. So definition, the vacuum sector of the Carroll CFT is the underlying vector space of this object 1. And I'm going to be referring to it a bunch of times, and I will call it H sub 0. That's by definition this thing. Typically infinite dimensional, and it's a thing which is equipped with just as many symmetries as the disk had, because it's defined just in terms of the disk. In particular, rotations acts on this thing. And if you look at the algebraic direct sum of the eigenspaces of the rotation operator, that vector space is the one that carries a vertex algebra structure. So that's the connection between Segal CFTs and vertex algebras. Now, vertex algebras have a distinguished element that you might want to call 1. So there's an element 1 in here. So let me tell you what that is. That's called the vacuum vector. So I'm not going to call it 1 because there's enough 1s. I'm going to call it omega is by definition. Now I'm going to use this piece of data. And I'm going to say, well, what do I have here? I have, starting from an object here. So what was my object? My object was this object here. Then I get a linear map from this. What is this? That's the underlying vector space of my object. Well, that's the thing that really now is the complex numbers. This was a sort of abstract unit of this thing, and that's the concrete vector space that has elements. So now I'm going to get a linear map from the complex numbers to this thing. And what is that? That is really just the same thing. I mean, you just, like, U is here, and then you unpack this definition here. What is that? That is, where is it? It is the image of this under that. That's exactly what you have here. The stuff in red is exactly this. So we have, it's Z sub disk of 1, where 1 is now the element 1 inside C. So in C we have 1. And that is called the vacuum vector. And that's an element of the vacuum sector. Okay. I hope that wasn't too confusing. There's also sectors which are not the vacuum sector. There's so-called charge sectors. And these are the vector spaces U lambda, where lambda is no longer this distinguished element in here. If I take some other element, an arbitrary element, I take another element, lambda, in here, I can look at U of lambda, and that would be here. I'd squeeze it in here. If I write, that is something that I would call charged sector. So this is. So a CFT has many sectors. These are various infinite dimensional vector spaces. One of them is distinguished. It is the vacuum sector. It's this one. And the other ones are, well, they depend on an object. Yes?
Could you please repeat what is U of one empty set?
Sorry?
Could you please repeat what is U of one empty set?
U of one empty set. Yes. One empty set is a distinguished element in the category C empty set. What is C empty set? It is the trivial category. It's just the category of vector spaces. That's one of the axioms. When you say for every one manifold you want a category, then you say that if you have the disjoint union of two one manifolds, you want the tensor product of categories. If I have a disjoint union of n different circles, I get the nth tensor power of this thing, assuming this was like a single circle. Take n to be 0. The tensor product of 0 many things is the thing such that if you tensor with that, you do nothing. I mean, this is the 0th tensor power of the category assigned to a circle. And OK, that's my category. It has a distinguished object, the complex numbers. I mean, it's literally the category of vector spaces. It has a distinguished object. But this side of things is when you think of it abstractly. It's like it's just a category with a distinguished object. And this side of things is when you think of this concretely. It's like actual vector spaces. And so the functor u, the underlying vector space functor, is the thing that goes from here to here. And if you open the definitions, it's a functor that does nothing. It's a functor that, by definition, takes a vector space as input and produces itself as output. But I find it useful to introduce notation that, to me, means I'm thinking of this as an abstract object, or I'm thinking of this as a concrete object. And if you have something concrete, it makes sense to talk about elements. And if you have something abstract, that's when you shouldn't use this notation. I mean, these by definition are the same. But yeah, so U of one sub-empty set is the complex numbers. OK, vacuum sector, vacuum vector. The charge sectors do not have any distinguished vector in them. So that's the thing that distinguishes charge from the vacuum. So what are the symmetries of any given sector? Well, if you look here at 3b, there's a certain semigroup that acts on any charged sector. Like it's essentially in the axioms that you have a thing, and moreover, this action should be holomorphic. But in particular, there's an action. So that's the thing that exists always. But when your sector is the vacuum sector, you can be a bit more specific, because that was constructed in a way that, so for example, let's look at rotations. Rotations is, OK, so the semigroup of annuli contains as a subgroup the group of diffeomorphisms of the circle. These are annuli that have no interior whatsoever. And that's a group that has a central extension by U1 cross Z. And in that group, there is a subgroup which is just rotations. So rotations will act, and that at the circle group is a very, very simple group. This C star part of the central extension now becomes a trivial central extension, but the Z part remains non-trivial. It is the universal cover of S1. So rotations act here, but they act. But if you go around 2 pi, it's not the identity, or not necessarily the identity. Here, on the other hand, the vacuum sector was constructed completely functorially out of this manifold, and that manifold does have S1 symmetry. And so here, on the vacuum sector, this Z part goes away. The action of this thing factors to an action of a certain quotient where you mod out by the Z. So that's a thing that you learn. And there's another, so this is, that's one of the things one can say. But there's something else I can say, which is there's a certain important subgroup of the, or sub-semigroup, sorry. Whenever I say group, you should think that it could be a semigroup, of the semigroup of annuli, which is the, let's see, like that. So if I look at the set of holomorphic maps, from D to D, which are, well, I don't want like holomorphic maps, I want holomorphic embeddings. Holomorphic embeddings from D to D. So things that map the disk to itself, not necessarily surjectively, but I mean, it could be like shrinking by something, or there's a name for these things in complex analysis. These are called univalent maps. So I'm going to call this univ. That's like for univalent, not for universal. There's a semi-group structure on that, obviously, because I can compose maps. And there's a map also from this to analyze. Well, what do you do? Suppose I have one of these maps. It sends the round disk to itself, but the image of the map might be, so it sort of maps it. So that's the image of my map, so call this map psi. Then this is, in red, I have written psi of V is this small thing. And well, I see an analyst there. And the analyst is the stuff in between. And so this is the analyst that you can get. So the stuff in between, the stuff that's here, that is an analyst that depends on psi. And it's an analyst with parameterized boundary. The circle on the outside is parameterized by the identity map, and the circle on the inside is parameterized by the map psi restricted to the circle there. And therefore, it's a good element of the semi-group of analyte. Analyte have parameterized boundary, otherwise you can't compose. Not everything is of that form. And specifically, if the Lie algebra of this, that was this Witt algebra that has all these LNs, or N in Z. So recall that the Lie algebra of an S1 is spanned by these elements Ln. That's a Witt algebra, and the Lie algebra of univalent is the span of ln's for a subset, and n bigger equal than -1. And if you remember the specific formula for the Virasoro cocycle, the cocycle that defines the central extension of this, it happens that it vanishes identically on this sub-Lie algebra. And so that's a thing that admits a canonical lift to the central extension. This is not a thing that acts on the vacuum sector, but this thing is a thing that has a chance of acting because the cocycle is gone. And let me tell you how it acts. Here's squeeze it there. Does that make any sense to try to squeeze it there? Okay, so here's how it goes. So I fix an element psi, and then I'm going to construct a map from the vacuum sector to the vacuum sector. I'll start with H naught, whose definition I'm going to recall because it's gone behind this board. It is F sub disk of 1 sub empty. That's my definition. What can I do? Well, I can apply what I have. Namely, I have Z sub A psi. A psi being this analyst that I have built that goes from this underlying vector space, and then you fit in F sub A psi. And then you copy what you have there. F sub disk, 1 sub empty. OK, now here's an interesting thing. If I take A psi and stick in a disk into it, well, here it is. I have A psi, and I stick in a disk into it using the parameterization. That's exactly recovering the disk again. So this is canonically the same thing as, so that is equal to F sub A psi with a disk glued into it, which is the same thing as F sub disk. So what do I have? I have U of F sub disk of this thing. That's the same thing as that. And so here we go. I have a map from the vacuum sector to the vacuum sector associated to any one of these univalent maps. And there was no anomaly. You can sort of see that this thing acts naturally.
Yesterday you were saying that there's a problem with gluing for things such as these. Do I have to worry about this gluing?
I'm taking the approach that we are now given one of those, and I'm going to tell you what you can get from these axioms. So I'm no longer trying to construct something that fits into these axioms. I'm saying, OK, suppose we do have a thing that has all this. Then here are some things that I can name and things that I can do. And one thing you can do is define the vacuum sector and the vacuum vector. Another thing you can do is construct a specific action of this sub-semigroup on the vacuum. And here it goes. This is how you do it. And the fact that it is possible to do it is not surprising, given that the Lie algebra is just a piece of the Lie algebra where the cocycle trivializes. You sort of know abstractly that it should be possible. And this is a thing where you can now do it concretely. And this is the formula for doing it concretely. OK. So the next thing that I want to tell you about is quantum fields. So, I mean, after all, this is conformal field theory, so we need the fields somewhere. OK. Definition. Primary field of conformal dimension delta that's one of these things that physicists write as phi of z. They sort of like just write the thing and work with it without necessarily always asking exactly what it is. So these are like really the basic things that you work with. But what is one of these? well, is a gadget phi. That assigns to every complex cobordism sigma equipped with points z1 up to zn in sigma, and tangent vectors at these points. So the tangent vector at the point zi is called vi. And to every object lambda in so I'm going to write something that looks very similar to this item in this box here, in box 2b. And lambda in the incoming boundary of sigma, this thing that I called S1. So it assigns to every one of these a linear map Z sub sigma modified by all these things. So I write a comma and then I write phi of Z1, comma V1, phi of Zn, comma Vn, and that's a map from U of lambda to U of F sigma of lambda. Okay, some axioms. So these are homogeneous of degree delta, meaning that if I take one of these, I guess I can write the equation. So Z sub dot 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 dot, and somewhere in the middle, phi I, as opposed to writing phi I of Z I V, I write, and then I put a scalar here. That should be the same thing as A to the delta, and then Z, and then the same thing without the scalar. So Z I V I. So it is depends on these variables V in this specified way. And the Z blah 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 agree with the old Z when n equals 0. So if you don't put any field insertions, there's already a thing called Z. You're not allowed to change that. So this is providing extra data that whenever you put field insertions, you get new maps. And moreover, these new maps should satisfy all the very same axioms that we had for this now in the presence of field insertions. If I have a cobordism with a bunch of things, with a bunch of points, and another one with a bunch of points, compose. Essentially, you copy all the axioms and you put extra insertions. And the new thing that you put is this condition about the dependence on the vector. So if someone, for example, if me in the immediate future writes phi of z, the vector is always there implicitly. But sometimes you sort of get tired of writing these very long expressions and you just write phi of z. But it means that there's always a vector somewhere because and that things transform in this particular way, like they satisfy this rule. Now there is a very important result called the state field correspondence that say that there's a bijection between fields and elements of the vacuum sector. Well, not elements, elements of a particular type. If you want to have a correspondence that works with every element, then you need to remove the word primary. But let me first do it for primary things. Theorem. State field correspondence. It says that primary fields of conformal dimension, delta, are in bijective correspondence with states, by which I mean elements of the vacuum sector, satisfying L0 of xc equals delta xc. So they have to be eigenvectors for the eigenvalue delta, and Ln of xc equals 0 for all n bigger than 0. And that's what makes these fields primary. So they're lowest energy vectors for the action of Virasoro. That corresponds to the notion of highest weight vector in representation of Lie algebras. It's the thing that's at the very end of your representation. So let me tell you a little bit how that goes. First of all, if I have a primary field, how do I get an element xc? Well, that's fairly easy. So to go in that direction, you define xc to be, and I'll first draw a picture and then write a formula. Take the disk, and at the point 0, so this is the standard disk. At the point 0, I'm going to put the field phi. And that's now a thing which I claim is an element of H0. So let's write it in formulas. That's going to be Z sub. So we're copying essentially the definition of the vacuum vector, except with a field insertion. That's going to give us a chosen. So it's going to be D, comma, phi of So I need a point and a vector. My point is the point in the middle. My vector is the standard unit vector. I'm not going to put my vector to be 0 because otherwise it would produce 0. And then, so phi of 0, 1, all that of 1. And that's an element in H0. That's by the same reasoning here. It's an element in here. How do you go the other way? How do you given a vector, how do you produce these things here? Okay, so suppose I have one of these setups. I have a surface with a whole bunch of points and a whole bunch of vectors, and I need to do something with that. Okay, so we have our surface. Here it is. Might have some genus, and it has a bunch of points, Z1 up to Zn. And I want to put the field phi, but I don't have phi. What I have is this vector, C. So here's what you do. You choose disks, namely you choose maps from the standard disk into sigma. So these are maps Fi from D into sigma with a property that 0 maps to Zi. And if it was possible to further arrange that the standard tangent vector 1 maps to Vi, then that would be good. That would make my life a little bit easier in writing down what I have to write further down. But you can't really arrange it. I mean, if you have many points that are close by, and if these vectors are really big, then it's just not possible to arrange that the disks map without overlapping. So, okay, you just have this one condition, and then we're going to fix the formula by using this relation. So then we define this thing here to be, okay, what do I have? I have a surface sigma, and I have these disks. I'm going to take the surface without the disks, and I call that sigma 0. So sigma 0 is sigma minus the image of the Fi's, or minus the image of the interior of the disks under Fi. Okay, so Z sub sigma 0 of, so what is the boundary of sigma 0? It has 3 types of boundary. 1, 2, and these disks. I'm going to treat these disks, these circles, as incoming boundary, stuff that I can put something there. And what am I going to put? going to put that vector xc over there. So it's going to be, I put xc, tensor xc, so n times, and then this thing here should be a map. So I'm going to leave this slot open so that this formula defines a map. It's a thing that if I take an element in here, I put it there, and then I will get an element of that. And then there's a correcting factor to account for the fact that these fi's didn't have the correct derivative. That's going to be the product I equals 1 up to n of the ratio between vi and f prime I at 0. And that whole thing is to the power delta, because it's fields of control dimension delta. OK, and there's like a little check to see, well, that it didn't depend on the choice of fi. So what you do, you have to say, well, suppose I take my disk and I make it a bit bigger or a bit smaller. Then what? How do you show that this formula remains the same? And
sorry, I probably missed that. So, but you print back bi, the beta bi to unit disk and treating it as a complex number. So what's the meaning of this?
vi is an element of
tangent.
the tangent space in sigma, and the derivative
Yeah, so it's also a tangent.
is also a tangent vector, and these two things being elements of the same one-dimensional complex vector space, I can take the ratio, and that's now a scalar. That scalar I can raise to the power. Anyway, so you sort of like take this disk and make them bigger and make them smaller, and when you have like a small disk inside a big disk, that's exactly the situation of having an element of this group of univalent maps. And then, well, that's part of the argument that I'm not going to get into that eventually shows that this is independent.
Sorry, so conceptually, so was there some kind of consistency condition between the defined points? So we have to define z of sigma, phi, ci, di for all points, right?
Oh yeah, these are unordered.
Yeah. But actually, I don't know. Well, maybe so, is there some sort of consistency condition? So when you start to move these points di around, is there some kind of consistency condition?
If you move the points around, so if you think about, so this tells you about the dependence on v. If you change the zi's, and you think about the zi dependence, then it follows from this axiom here, this holomorphicity axiom. It follows that the zi dependence is holomorphic. So as you vary zi, this map, which is always a map from the same thing to the same thing, varies holomorphically in the zi parameter.
But there's nothing like sort of factorization of adding points one after another using some kind of this.
Well, yes, there is. There is a formula that, so the formula z sub sigma 1 union sigma 2 equals z of sigma 1 compose z of sigma 2. That formula, which is part of the axioms of Segal CFT, is also an axiom of the notion of primary field, where you now decorate the sigmas with extra field insertions. So that's the condition that. So I wasn't complete in my definition. You have to say this, and also something for disjoint unions. I mean, like, essentially, you take all the definition and you sort of copy it. So these are the primary fields, and these only work under this assumption here that the LNs are act 0 when for all these energy lowering operators. But you can also imagine writing that same formula like this procedure here looks like it's fairly general. You take your surface, you remove some holes, and then you write down this thing, and then you're like, okay, well, this maybe isn't completely invariant. I need to make it invariant, and then you add a factor that fixes it and makes it invariant. And then the question is, what does this correction factor end up looking like when you don't have this thing here? So let me say why this is just, OK, so we're going to generalize the notion of field in 2 directions. One of them is we're going to relax this condition here. And the other one is we're going to explore what happens if I take C to be an element of a charge sector. Yeah.
For these conditions to sort of see where they end up with the field, I guess L0 is sort of infinitesimal rescaling, which gives you the scaling invariance.
Mm-hmm.
Ln, I mean, should I think of this as sort of infinitesimal little rotations, or why do I see in this condition say?
Let's see. It's here. So we look at maps from a disk into sigma with one particular condition. 0 goes to a specified point. So this condition means that we don't care about all univalent maps. We only care about univalent maps that fix 0. And therefore, that's going to have the effect of changing this from n bigger equal -1 to n bigger equals 0. So that's a relevant semi-group that's going to control the freedom of choosing these maps. And now we want to look at what happens to this vector xc when we act on it with that semi-group, which is slightly bigger, slightly smaller than that, like only starts at 0. And this is saying that it generates a one-dimensional representation. For L0, we know how it acts. For Ln's, we know how it acts. And that one-dimensional representation is exactly the thing that ends up being put there as this correction factor to the formula. So if you drop this condition and say, well, now I'm going to, so the vector spaces we're talking about always have positive energy, meaning that if n becomes bigger enough, these operators lower energy by n. So if n becomes big enough, it will be 0. But C might generate a representation which is not one-dimensional, which has like a given, like it's like finite dimensional of a given dimension. And then one ends up needing to put a form, like a term here that makes an explicit reference to that representation. OK, so what I wanted to say is that there's 2 ways of generalizing the notion of quantum field. One of them is to allow for elements that live not in H0, but in some charge sector. And then if you do that, That's called a charged field. So you write the same type of formula, and you define it using the same type of way. And then what ends up happening is that it no longer lands here. It lands in something that now is affected by the charges of the various fields that you put there. By the way, if I have, there's nothing that tells me that I need to put the same vector at any given point. You can take a bunch of vectors and put, like, it can put a field here and another field there, and then this formula will just work. So there's an easy modification of this, which is just say like C1 and then Cn, and then here each one are going to have their own conformal dimension. So here you do this, where this is the conformal dimension of Ci. So this is the thing you can do. And so for charged fields, this gets modified when the fields are charged, i.e. when you put another vector space there. And when we modify this condition here, then you need to change this. You no longer can express everything in terms of just a tangent vector, but suppose that I have, well, L0, we know how it acts, and suppose that L1 acts in a non-zero way. If L1 acts in a non-zero way, then I need a tangent vector plus some second order information. So you need a local coordinate of higher order at that point in order to be able to make sense of this. And so you have, now you have so the VIs are now local coordinates up to order D. And what are we doing here? Where we have a local coordinate on one side and a local coordinate on the other side, and we can compare these two local coordinates. And this ratio now becomes an element of a Lie group, becomes an element of, so this thing here, as written, is in C star. But then if you pass from okay, so if you relax that condition in green, these are then called, let me try to stick to one color coding, they're called descendant fields. So then you go remove this, and they're called descendant fields. So if you now want to look at descendant fields, then this group gets replaced by the group of automorphisms of local coordinates up to a given degree. So that's automorphisms of C adjoint Z modulo Z to the D plus 1. That's a finite dimensional algebraic group, and you end up having to take an element in this group and let it act in order to so this equation here, now you have an element of that group over here, and you have a representation that appears let's see if I can say something that's coherent the amount of time that I have. You can't put it at this place in the formula because it doesn't really make sense to take a representation and let it act on this thing or to raise it to power. You need to take it and let it in front of the little x's. So the formula that replaces this in the case of descendant fields looks as follows. So we have, Z of sigma, comma, phi1 of Z1, comma. Well, now that's not going to be a vector, it's going to be a little jet up to a given order. So let me call it J or jet. Then you do the same thing as this. So you pick maps, Fi like that, and then you write something that's going to be Z sub the punctured thing. And now you put G1, C1, tensor Gn, Cn, tensor dash, just like I had tensor dash here, where Gi is Fi inverse composed with Ji. And that's now an element of this group of, let's call this G sub D, of G sub D. So the thing is that this group here is exactly the group whose Lie algebra is this part of the Virasoro algebra that's spanned by L0, L1, up to LD. That quotient of the Virasoro algebra of this. So you take this Lie algebra, throw out L0, throw out L minus 1, so start at L0. That has like L0, L1, and so on. And then you mod out by the things that are high enough. And that's a thing that ends up acting on the vectors that you have. And then, so that's a formula for descendant fields.
So what's the case of primarity corresponding to D equal 1 or 0?
Yeah, so if I take D equals 1, so I have a 1 jet, which is just a vector, or a non-zero vector. And then I have the group of automorphisms of C of Z modulo Z to the 1, i.e. just automorphisms of, did I do it right, or has it been?
Yeah, algebra.
Sorry.
C
of D equals 1. I have a 1 jet. C of Z modulo Z squared. And then the automorphisms of C of Z modulo Z squared can scale Z by a scalar. So that's then ends up being, so this C cross is the case D equals 1. And the relevant Lie algebra has L0, L1, up to L sub D minus 1. Okay, very good. That's
are the states corresponding to primary fields guaranteed to exist, or do primary fields always exist such that you always find the highest weight vector?
there's one which always exists, which is the vacuum. The vacuum is at the very bottom, and if you lower its energy, it's 0. So that's a thing that exists. That's the only one that's guaranteed to exist. There exist models, for example, the minimal models, where the vacuum is the only primary field. And therefore, in order to describe a collection of fields that generates your theory, you're forced to consider things that don't satisfy this. So when you have just the minimal model, so you just have Virasoro, the generating field in that case, which is often called the stress energy tensor, will require to be looking at jets of order 3. So we're looking at formulas that end up involving third derivatives when you write them down. But for any chiral-conformal field theory that you can think of, it is always the case that it is generated by this stress energy tensor. That's a bit annoying to write down, and a bunch of primary fields.
Could you please be more specific when we say that phi is a gadget?
Sorry?
Like when we say that phi is a gadget, it's just like a notation trick?
Phi is a gadget. You don't like this word.
Well, I'm just confused because I don't know what it means.
Is a map? Is a function? Is a So I mean, if I say a linear map from V to W is a gadget that to every element of V produces an element of W and satisfies that list of axioms, that's just a word that I'm using that means it's a map. So when I say phi is a gadget, I just mean phi is a thing which assigns to every, and then I say what it takes as input, and then I write what it does as output. It's like it produces a linear map. And then those linear maps. So it's phi is a collection of linear maps of that form indexed by sigma, a bunch of points, and a bunch of vectors, satisfying some axioms of which I wrote one here, and I sketched one there, and there's some more.
I have a question for something that you said very early on. Why does the annulus monoid not act on H0? Or I mean, does it give linear maps that just form a projective representation, or does it actually not map H0 to H0?
It does map. So not just on H0. So H0 is the underlying vector space. H0 is a special case of this. This is H0, and that's a charge sector. And for any charge sector, for any one of those vector spaces, there's a map from the annuli to the semi-group of linear maps from that vector space to itself. So yes, it acts. But of course, it's not this thing that acts. It's the centrally extended thing that acts. When you pass to the sub-semi-group of univalent maps, then the action is an honest action. And the fact that it's an honest action ends up being important when we write this thing here. So what is this? This is an element of this group. How do I, so the Lie algebra of this group is the span of L0, L1, up to LD minus 1. in order to know how an element of the group acts, I need to know how an element of the Lie algebra acts. In order to know how an element of the Lie algebra acts, I need to have it on the nose, not up to central extension. And that's why it's important to pass a setup where it's not this, but that.
Any more questions? Thank André again. We'll resume in 10 minutes.
Yes?
I can understand.
Yes, the psi and the sigma. Yeah. Yeah. So that's also, there's 3 possible charges, the vacuum. So